Yesh and Hyungyu for the invitation to give a talk and for organizing this really wonderful conference. So what I'm gonna do, I think I click on this, yeah? Move the slides from,
yes.
Okay, well, I don't know about the mouse. Okay, so what I'm gonna do, this is like a big overview of what I'm gonna talk about. So you start out with objects, and then we're gonna construct some cobordisms. We start out with objects, and cobordisms are gonna be maps of some isotopy, and then we're gonna cook up some algebraic invariants. And what you're gonna see is that when you have manifolds, we're gonna construct, there's cobordisms associated to manifolds. And then as you have seen before yesterday, today, and then maybe from other talks, that whenever you have links and foams, we can come up with link homology. And then when you have decorated foams, what we do is we can study K-theory in the perspective of decorated foams. So now a question is, what algebraic theories can be studied by decorated singular cobordisms? So here's the outline of today's talk. What I'm gonna do is I'm gonna talk about weighted one-dimensional foams, and then I'll talk about SAF, invariant, and then the K0, K1, the groups, and then higher foams and higher K-theory. So first, I'm going to talk about this first paper, SAF invariants and foam cobordisms, and just this joint paper with Mikhail Khovanov. So what is the algebraic invariant of a weighted foam of the cobordism? So whenever you have cobordism classes of weighted one foams, these are isomorphic to R, wedge R, and the wedge is taken over the integers. And on the right-hand side, that's what you call SAF invariant. And keep this in mind throughout this talk. So here's some notations. I don't know how many of you are familiar with foams. No. Okay, at least one person is brave enough, or two people. Okay, good. So please let me know if you need more examples during the talk. When I say one foams, those are talking about one-dimensional foams are basically graphs. Think of any kind of graph. So this has vertices and just edges. And then two foams or two-dimensional foams, meaning these are, example, the picture in front of you, that's called a two-foam, two-dimensional. You have a surface, edges, and the vertices. The goal is to study one foams, which are oriented and has weight trivalent graphs. So graphs are like edges are kind of merging in, so that's trivalent vertex, and then two edges are merging in towards that vertex and one edge merging out. Or you can have a split. You have one edge and then two edges coming out of a vertex. And the vertex, whenever you have three edges, on that vertex, those are called trivalent. So our goal, what we want to do is we want to study one foams and two foams, and then suitable cobordisms between them. So let's say you have a whole bunch of points to another whole bunch of points. You want to study all sorts of maps between them, and what you should think of would be a bunch of strings. And then what we're going to do is the strings will have orientation. We're going to read from bottom to top. And you can concatenate from left and right. Yes.
Through definitions, it's a trivalent graph, but two vertices are on one side and one vertex is on the other side. Should I think of it that way? And then the weights add up?
One edge, one side, two edge, the other side.
Yes.
Right.
And are the weights supposed to add up?
Yes, they're supposed to add up. Exactly, that's exactly right. Yeah. This picture here, this is an example of a weighted two foams. The weighted because each piece of the surface, it has a weight. So this guy up here, it has a weight A. This guy has weight B. These two guys are sort of merging in together, and that's going to cook up a surface of weight A plus B. And then same thing here. This surface and this surface A plus B, A and B plus C, they merge it together, and they're going to give you a surface of weight A plus B plus C. And that would be the surface in the back. So this is an example of a weighted two foams, and this is equivalent to branched surface. And in the picture, what we see is we see a singular point here. So this whole thing is like a local neighborhood. You can sort of cut things out, remove everything else on the outside. You zoom in, and then you see a singular point of a two foam, and the singular point is right there. Okay. Also, the left two images. So now here, over there, so I could draw like a vertex, make it more explicit, but this here, this is a trivalent vertex, and you have two lines merging in and the one line coming out. It's a trivalent vertex where you have a line of weight A, line of weight B, and then they add together to give you a line of weight A plus B. And then the other way around, you have a vertex here, and then you have a split. Lines are sort of splitting, so one of the value will be A, the other value will be B. Of weighted one foams, for the right, you have neighborhoods of a point near a seam. So seam would be like, this is all the points here. This is called a seam line. All the points there are called seam lines. So you have neighborhoods of a point near a seam of weighted two foam. So these two are two foams. Each vertex of a one foam is trivalent, and the two edges are pointing in, and the one edge is pointing out, and then this will be the other way around. The weight preservation, just like what Richard was saying, you have A wedge and then the B wedge, A line, B line, and then they merge together to give you, and then the weights are being preserved. Okay, now something different is that what we're gonna do is you put an arrow. You have this arrow here that's going from A to B, and what this means is which one comes first. How do you do that? So you have to be very specific. So you draw like little arrow like this to mean A comes first and the B comes second, and the same thing here, same thing here, same thing in all the surfaces. So this is the order condition on the two strands that enter or leave a vertex. So these two lines are entering a vertex, these two lines are leaving the vertex. And then it's the exact same thing. You have this arrow here, which is saying the surface with the weight A appears first before the surface of weight B. So you have this arrow pointing in that direction. You also have this guy here pointing in the other direction. So we just have to specify this.
This is the same thing to giving the orientation?
Yes, you're giving a...
And all the faces?
Yes, you're giving all the orientation for all the faces relative to each other. Exactly right. And the same thing with the lines. You're giving an orientation, which one appears before, which one is first and which one appears second. Yeah. So we do this pairwise. Okay, so whenever I talk about one foams, these are going to be closed, like one skeleton. Think about that. And then circles without vertices are allowed. And then we could think of these as components of one foam. The two foam has facets, edges, and vertices. So you have surfaces, edges, and vertices. The facets carry weights, a positive real number. Two facets can merge along one seam, and then you can add the weights are additive. So I think I sort of talked about this. A plus B plus C, you can merge in multiple ways. You could do A plus B first and then add to that C. Or you could do B plus C first, like the surfaces with weights B and C first, and then you add to the surface of weight A. So that's what this next one is. A two foam is viewed.
So thickness is the same as weight?
Thickness is the same as weight, exactly. Yes, yes. A two foam is viewed as a cobordism between one foams. So you can sort of think of as one skeleton, and the maps between, you get a two foam in the middle.
Is that picture in the previous slide the unique type of vertex you're allowed in a two foam?
You mean here?
Before. That one.
Oh, yes, but I didn't, yeah.
Is that the only kind of vertex you're allowing?
At least on the surfaces, yes. These are the only vertices that we are allowing. We could add more decorations, more vertices, and then these vertices, codimension 0, codimension 1, lines and like dots or vertices, these are called defects. So we can add more and more defects in order to get like more invariants, but that'll come later. Yes. Good point. And then notice that like some of the pictures, we don't have orientations. That means, but what we can do is we can always go back and fill in with all these orientations on the surfaces and on the, relative to the surfaces, one from one to the other. So here on the left, this is an example of a weighted oriented one foam. So this foam is an example of a boundary of a two foam with a single vertex. Associativity flip between two ways to merge A and B and C into A plus B plus C. So this is a closed foams, and this is just a local snapshot picture of a two foam.
Sorry, how were they related again?
I think you have to cut this like locally and sort of bend things around, and it should be similar to this picture here. Yeah. It's actually in our paper, like there's a dotted line like this. It goes through only this part, and then we have to sort of match up. Yeah. So what we want to do is we want to study one foams modular cobordisms, which are two foams. One foams modular cobordisms, they give us an abelian group. Addition of one foams is given by disjoint union. The zero element is represented by the empty one foam. And then the minus one foam is basically means you just reverse the orientation. So in our paper, in our SAF paper, the group of weighted one foams modular cobordisms is naturally isomorphic to this SAF invariant R wedge R over the integers. The map from one foams to the cobordism group is reminiscent of the linking number that's related to SAF invariant of interval exchange transformation that we have seen in dynamics. Yes?
You talked about two foams without boundary, but what's a two foam with boundary?
Was a two foam with boundary?
Right. When you talk about a cobordism, does that mean that the boundary is a one foam?
Oh, the boundary is a one foam. Yes, yes. So what we're going to do is when you see something like this, the one on the left, this one is a closed, this is a closed one foam. But what you can do is you can take slices, and when you take slices any way you want, what you should see will be zero-dimensional vertices to another set of zero-dimensional vertices and the maps between them.
Is the one on the left the boundary of the guy on the right?
So this, the boundary of this guy?
Yes.
No, this is not closed. This one is not closed. This is just a local picture.
What's not closed?
The picture on the right is not closed because these are infinite like surfaces. They just go on forever. But then this guy here is closed. And you'll see later that we can work with the...
What's a two foam with boundary?
A two foam with, that's an example of a two foam with boundary.
So it isn't.
Yes, 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 yes.
Did you say that? Did you not say before though that the left one was the boundary of the right? No.
But the left one, it will be. You could sort of think of they're sort of related. But then what we need to do is we need to cut out this. We need to cut out just inside interior of it, and then sort of do a matchup between the two. But then this one is a closed up version of closed up version. And this is one dimension up compared to this also. Yeah. Let's take a look at one dimension lower. Let's look at weighted zero foams. So what are zero foams? These are going to be signed weighted points. So you have points here. So here, this is the boundary. What you've seen before will be like a closed one foam. But what you do is you just slice it. So that's what the dotted lines mean. These are not closed. You're just taking a piece of it. And all the points, all these points here, whenever you take a slice, it has a weight, A or B, and it has a sign, plus sign or minus sign. So here, as you can see, let me see, the cobordism group of zero foams is the real numbers, and then we take a zero foam to the sum of the weights of the signs. So like here, you can see, here's an edge, A, and then now at this vertex, at this trivalent vertex, we have a split. So this guy here is A minus B, and this other guy here must be B because they have to add up to be A. And then this is a picture, locally, this is the cobordism we have, only if A is greater than B. And then if this edge, all the points here have plus sign, then this guy here would also have a plus sign. And then this other guy that splits off, we could make it turn back, but it would have, all these points here would have value of minus sign. If A is equal to B, what we do is we should have locally, the picture should look like this. They can turn back, and then all the points here would have plus sign, and all the guys here would have a minus sign, and the weight would remain as A. And then for this guy, In this case, let's just say the weight B is bigger than A. And in that case, you have this, you could split things off, or you could sort of think of it as a merge. But then since B is pointing downwards, the smaller value will split off, going this way, and then the rest of it, B minus A would be coming, it would be all these points, would be valued at B minus A with a minus sign. So it will be the same sign as this edge. Question?
So picking up on the first one,
Yeah.
A is the weight on the edge and also the weight at the point at the
So-
bottom of that edge?
Right, so A would be it would be the weight at the point on the bottom, But you could take many, many slices, right? So what you can do is you could take another slice here, cut another slice there. So locally, you could erase all this picture, and locally, you would just be looking at this guy here, locally. So you could sort of think of it as the value A would be at the vertex, at the end vertices, at the end points. But then it's actually the weight A is given by the weight A is on every single point on the edge. So the value of A,
So the weight of the edge is what? Is A?
is A, yes, yeah. Interval exchange transformation, so what we have seen yesterday and today. What does that mean? What you want to do is you start with an interval of length 1. Let's break it into R pieces, lambda 1 up to lambda R. Each one of them will be between 0 and 1. And then the sum of these guys will add to 1. And what we can do is we can permute them. So here's an example. You start with a 0, 1 interval, and then you break it into 3 pieces. The first one would have 0 to A to A plus B to 1. And then what you can do is you can permute them and then rearrange it. So you could do A plus B, comma 1 first, and then 0, comma A, and then A, comma A plus B. So this is called interval exchange transformation. And what we do is we assign to these guys weighted 1 foam. And then what you do is you cook up SAF invariants. You can produce SAF invariants from the 1 foams. So here it is. Interval exchange transformations. It constitutes a large group G, so G modulo the commutator. This is isomorphic to R, the real numbers, X, wedge, the real numbers. The map from G to closed 1 foams, it takes modulo the cobordisms. What we do is we take commutators to no cobordant foams. So what we do is we take commutators to no cobordant foams. So basically, what you do is the graph might look very messy. And what you want to do is you want to pull things apart where things below, they all add to 1. And then here, what you put all the splits. So you see lambda, you see like a first split happening at this vertex, trivalent vertex, and another split happening right there. And then all these guys are merged, like these edges are all merging together. In the middle, you have all the sigma, all the permutations happening with all the intervals. So this is called F lambda sigma. This cobordism is called F lambda and the comma sigma, where sigma is all the permutation that's happening. And then the one with the hat basically means you get the top and the bottom and then you glue them together, you close it up. And that's what it means to close up. We have a closed up graph.
Sorry, the weights are related to the length of subintervals?
You mean the length?
The
Yeah,
weights
yes.
of the
Yes,
integrated
exactly, yeah.
How do you choose how to do the branching?
You mean like here in this picture?
Yeah.
Oh, so this is odd. Everything is up to isotopy, so you can move things around.
Right.
So even though you do a lot of transformations or untwisting, you'll see later on that the value, the SAF invariant, you're still gonna get the exact same, the invariant will come up.
I think the question's about, so if you go back a step, can
Yeah.
you show us the foam that you get from that IET?
You mean go back here or more?
Yeah,
One more.
Can you show us, what foam do you get from this?
This is not really,
It's the one you just showed.
Is this the one you just,
So here, the picture, it might not match up correctly, but then it's basically you have this you have an interval, you cut it into 3 pieces, and then you saw like the first one and the second and third got swapped, and then the first and the second one got swapped. And that's what you should see. I think this picture doesn't necessarily correspond to that because I added the example kind of late. Yes, and then that's the picture you should see. and then you close things up, and then you glue things back. Glue the endpoints. Yeah, good question. Okay, so now what we do is this corresponds to composition in the IET group. So as you can see, you have this closed one forms, and then you have another closed one form in the middle, and then you have this like a two form in the middle, right? From the bottom row to the second row, and the second row to the top row, you have even more. You have another two forms. And also keep in mind, we didn't add too many orientations on the like on the one skeleton, because that would be kind of, it might be too much. But there should be like orientations, pointing from left to right or so, and also like showing like another like arrow telling us which edge is coming before which edge. So there should be another orientation. To understand the cobordism class of this one foam, what we want to do is you get this one foam, you project it onto a plane, and then add local contributions with elements of R wedge R. So what we need to do is you need to come up with a notation, sort of kind of mess around with it, play around with it to see what notations work. So here you see that you have a split, and you have a split in the second column, and then you have a merge, and then you have this crossing. Or you have this you have a crossing on the last one, and you could see whenever you have a split with a clockwise, that contributes 0 at the trivalent vertex. The second one is a split but counterclockwise. It contributes B wedge A, and then you can see because of this orientation does matter. Now you have a merge and a merge. So the first one was clockwise. That gives you 0. Whenever you have a merge, or you have a counterclockwise, that must give you 0. So it's sort of like opposite. And then for the second and the fourth column, you have a counterclockwise that gives you B wedge A. You have a clockwise that gives you A wedge B. And then whenever you have a crossing, A line crosses with a B line, or edge crosses with B wedge. Whichever one comes first, whichever one's on the left, that gives us A wedge B. So a summary of that would be, so local decoration, what you want to do is locally analyze these cobordisms. So whenever you have a split clockwise, that's going to give us 0. And the split counterclockwise, that's going to give us B wedge A. That's the same thing as minus A wedge B. Now whenever you have a merge, so it's going to be the opposite. So here, the clockwise gives us 0. Counterclockwise is going to give us 0 for the merge. And then for the clockwise, it's going to give us A wedge B. And the crossing, if A is to the left of B, it's going to give us A wedge B. Since A is to the left of B, we're going to get A wedge B. So we see that A wedge B is minus B wedge A, and the A wedge A is equal to 0. And these two identities are exactly what makes new invariant under the local diagram moves. And I think in the next slide, I do have an example. So here, this is a closed one skeleton. This is a closed one form on the left. You have two trivalent vertices, 1 and 2. So I don't know if I have chalkboard space. Can I still use the chalkboard? Okay, wait, what am I? So let's do this one. So you have, let me see. So this is going down, down. That's an A, B. The middle one is A plus B. And then you have this orientation. Okay, so this vertex on the top, and then you have this vertex on the bottom. If you go back to the top, let's look at this. So which one is this? You have a so let's look at the top vertex. You have a split, and then this is a clockwise orientation. So you have a split. So it's going to be first one or the second one, where you have a clockwise orientation. So that the top vertex is going to contribute 0. This guy you have 0, and then for the bottom vertex, this guy on the bottom, you have a merge. So at this vertex on the bottom, it's a merge, but then the arrow's pointing clockwise. It's pointing to the left. So you should get A wedge B. So in my case, it's still A, the bottom guy has weight A, this guy has weight B, so you still have A wedge B. So this is what you have on the left. This is the one. And then for this other picture on the right, for this other one foam on the right, you have this guy. And then what you do is you close it up, something like this. And then let's say this is A edge, here's A. And then I'll make it more smooth. So this guy's A, B, and then these guys come together, so you have A plus B. This edge has weight A plus B. And then what we want to do is the swap, or this orientation. So now let's go back to this. We have 3 of these vertices to analyze. So this vertex on the left, it looks like this one is a split and it's going clockwise. You have a split and then you're going clockwise. So this guy here is contributing 0. The one in the middle, this guy here, that's just a crossing line, so just crossing past each other. So that's going to give you A wedge B. And then the last guy, this vertex here, you have a merge. You have a merge, and then you're going counterclockwise. So this guy here is contributing 0. When you add them up, you get the same thing. So that's how you know they're cobordant to each other or they're isotopic to each other.
In the other slide, did I see you say that these two one foams are homeomorphic?
Yes, they're homeomorphic.
What do you mean by that?
That means we can go from,
In what sense are they homeomorphic?
They're homeomorphic, meaning what we can do is we can do some, there should be a map between one guy to the other. And then these guys are homeomorphic because they give us the same SAF invariant. And also there should be a way to untangle this mess to give us this guy. Or there should be a way, so what you can do is you can sort of unflip this and then move the outer vertices closer together and move things around to obtain this.
Well, the crossing is not a vertex.
Exactly, that's not a vertex. Right. Right, so we could do like local isotopies, and I think you'll see it later too. What are the isotopies you can do? So you can move things around, and at the end of you can simplify the pictures, all the one skeleton or the one foams, and at the end of the day, you're going to get the exact same invariance appearing. And this is very simple. Things are we just need weighted, oriented one foams to get the SAF invariance. Okay, so now these are some of the isotopies. So whenever you have lines merging, like crossing and then uncrossing, you can pull things apart. For the second one, you can just straighten things out. So whenever you have this like loops, bunch of loops and tangles, straighten things out. Or you could do calculations with all these loops, and things are going to simplify anyway. Number 3, you have this sort of like a braid relation, or like this associativity, right? Right. Huh?
They look like virtual Reidemeister moves.
Yes, virtual Reidemeister moves, exactly. Number 3, yeah. Whenever you have this, you keep the end vertices to be the same. So A's on the left, B's on the right, but you could swap things. So these are local isotopy moves. You could swap to get this guy here, or you can undo the swapping to get this. And then for this picture on the last one, you just slide this thing up and down, and you get the exact same invariants are preserved, basically. Okay, so here's some elementary cobordisms between one foams. So one foams, again, those are the one skeletons downstairs and upstairs, and you have 2 foams between. So whenever you have something like this, what you can do is you can pinch this. You can pinch this down, pinch like the cup down, so you can get it up to just one line of weight, A plus B. It's the same thing here for this guy here. Actually, this picture is giving you a 2-foam picture, and then this picture on the right is basically what we did is we take a slice of the bottom and then slice of the top, and What are the one skeletons? How do they look like? The second two pictures on the right, what you do is you have another cobordism between the two. And what this basically means is that you can pinch things down exactly the same. Here, these two guys are isotopic to each other. And then for this guy here, these two are also isotopic to each other. There might be more move. There might be a little bit more math to do, a little bit more work to do to show the last two. Like how are they isotopic to each other? When you compute SAF invariant, it should be exactly the same. But like, how do you do the local like stretch?
You mean cobordism or?
Cobordisms, isotopies and the cobordism. Yes, that's exactly right. So elementary cobordisms preserve SAF invariance of one foams, and then they generate cobordism equivalence relation on one foams. So basically, since these two guys are cobordant to each other, we have this one foam structure. And how does a one foam look like? The one foam would basically take one guy to the other guy, and then you just have to, you have the seam line here. This is a seam line, and here's another seam line where things are sort of, the surfaces are sort of glued on top of each other. And then you also have these two, they're cobordant to each other, and then whenever you have a circle, you can erase it. It becomes empty one cobordism. So notice that people normally study, when you think of mathematicians studying TQFT and maybe quantum field theory, what they do is they study n manifolds modulo n+1 dimensional cobordisms. And people like Renee Tom and many other people, what we're doing is we're studying cobordism groups for singular structures, and then including we have foams that are decorated by weights, together with this orientation, clockwise and counterclockwise orientation. If you're interested in the SAF paper, there's two papers. So the paper I just talked about will be the second one, foam cobordisms and the SAF invariant. And then this is related to foam cobordisms and then K theory. And that will be the second paper that I'm going to talk about next. Any questions so far? No. So geometrically, you've seen so far, you have these, the edges have weights, and you have this cutting and gluing happening locally, and that give us.
One question. So SAF was complete invariant of the cobordism
Yes.
class of the one foam?
Yeah, exactly. One foam with weights, and then you have to have like clockwise and counterclockwise. Whenever you have a trivalent vertex, you have to say which one is first, right? That's all you need. And you get SAF invariance. I would say if you're interested in like dynamical systems and then maybe foam cobordisms, you want to know how many other ways can things, like what other, these geometric ideas, how do they appear in terms of foams, like cobordisms? I would say that's completely open.
So if it's zero, it's null cobord.
If it's, what do you mean it's zero?
If its SAF invariant is zero, is it null cobordant?
It's no cobordant, exactly. Question, Steve, on the back?
Oh, yeah, your pictures all look just like branch surfaces from the work of Bob Williams. So these things look like cycles in hyperbolic dynamical systems. And so is your SAF invariant some sort of dynamical invariant
It is a dynamical invariant,
associated to hyperbolic systems, right?
I think,
I mean, it looks at that, the pictures are identical from the old days.
I mean, you don't have the weights.
What?
You don't have the edge weights in the system.
You have, he has weights, because these are the measured weights.
The weights of the invariant measure?
Yeah, when you look at Williams' work, these are the weights that are carried by the Anasov system, or the hyperbolic lamination.
Yeah. In that case, it's the same one.
okay.
Whatever.
Maybe I can talk to you afterwards to get this reference.
Okay.
Yes. Yeah, so geometrically, so far you've seen the top line, but algebraically now what we're gonna do is talk about projective modules and direct sums. That's gonna give us this K0 group. And then whenever you have this automorphism or monodromy and short exact sequences, that's going to give us this K1 group. And everything is in the context of cobordisms in terms of foams. So the main idea is that local geometric relations produce global abelian invariants. So now the next paper, algebraic K-theory and foam cobordisms, this is joined with David Gepner, Mikhail Khovanov, and Nitu Kitchloo. So consider oriented one foams as before, but now what we're going to do is you have this one foams, but each point is not decorated by projective module, finitely generated projective module over a fixed ring R. So in terms of algebraic geometry, let's just work over commutative ring R. In that case, finitely generated projective R modules correspond to vector spaces over the spec of R. And then more generally, we have finitely generated projective R modules, and they correspond to finite locally free sheaves over spec of R. So, and then what we see is K0 of R, we're recording stable differences of vector bundles, and then automorphisms of projective bundles are given. They give us information about K1 group, and then the foams are going to carry out all these informations geometrically. So what we're going to see is that whenever you think of projective modules, it's an algebraic analog of a vector bundle. So that's what you should think of.
What's the difference between the first two objects on the left-hand side?
Here?
I mean, they're the same thing?
Huh?
What's the difference between the first line and the second one?
What do you mean first line and second one?
Those that you outlined, finally generated projective R modules.
And then here and here.
Yeah.
Oh, no, they're very similar. They're just very similar. But what we're going to do is you should think of, whenever you think of projective R modules, you should also think of vector bundles over spec of R. But more generally, people don't have to work with vector bundles. They can work with locally free sheaves. Yeah. Yeah, which is the same. Yeah. The rank may vary from connected component to connected component. Okay, so now we have exactly the same one foams, but then every single vertex, even though we drew only one vertex here, all the vertices, all the points here are labeled by projective module P1. And then all the points here should be labeled by projective module P3. And then whenever you have a merge, all these guys are isomorphic to the direct sum of P1 and P3. So you have a merge, you have a trivalent vertex, and you have another trivalent vertex. And then here at this other trivalent vertex at the split, one guy is labeled by projective module P1, the other one is P3, and then since these guys are split, the one downstairs, that's labeled by the direct sum of P1 and P3. So what we want to do is whenever you have a trivalent vertex, you want to fix a direct sum decomposition. So this is very similar as before. We want to consider such foams with zero-dimensional boundary. So the zero-dimensional boundary is at the end. You should really think of the zero-dimensional points at the end points also. On the boundary, you have a sequences of signs and projective modules. So you have a plus sign. That's because the line is coming out of the boundary downstairs. And then if the line is turning backwards, all those points are labeled by, or that point, second P0 is labeled by minus sign. Same thing, whenever lines are emanating from downstairs, you have a plus sign, and then when you go upstairs, these guys are labeled by plus sign. K0 of R is an abelian group generated by symbols that look like this. P of finitely generated projective R modules, and then you have just one relation. Whenever you have P1 is isomorphic to P2 plus P3, you have this in K0, you have P1, the object P1 is equal to P2 plus P3. If R, commutative ring R is a field, then any projective module is isomorphic to K to the n for some n. And we know that K0 of a field is isomorphic to the set of integers. Any free module is projective, but any projective is not free. It doesn't go the other way around. It depends on the ring that you're working with. Should I go through this, or is everybody okay? Okay, it's okay? Okay. So decorated zero foams, basically means you have finite sequence of points with orientations plus or minus signs, and then finitely generated R module at each point. So what we want to do is you want to view the one foam with boundary as a cobordism between R decorated zero foams. The top and bottom zero foams, they define the same element of K0, and then here's our first main result. The Grothendieck group K0 of R of finitely generated R modules can be identified with the group of zero-dimensional decorated foams modulo cobordisms. So whenever you think of the group K0, you can actually reinterpret it in terms of zero-dimensional decorated foams modulo the cobordisms. So what we can do is we can think of our foams as carrying a flat connection with fibers. Let me see, okay. As projective modules, P are the fiber. So think of over each point, you have a projective module P, and then the question is, can we do this in higher dimensions? So now if you go one dimension up, you consider the group of one-dimensional foams, which decorations modulo cobordisms. What we do is whenever you have a disjoint, it's an abelian group with disjoint union as an addition, and you can bend foams to get the dual. U star is just is equal to minus of U. Near a vertex, this is a two foam, so near a vertex, they carry decorations by projective modules, P1, P2, P3, and their sums are also labeled. So you could sort of think of this as you have a surface P1 and P2, they merge together and they give us P12, which is the direct sum of the projective module. And then this guy here, here's two surfaces. Here's these two surfaces, they merge towards P123, and that's how we get that. These two surfaces, this guy and this guy, they merge together and they give us P23. And these two guys merge together and they give us P123, which is given by the direct sum P1, P2, P3.
So there's a particular orientation here that you've omitted.
Yes. Exactly right.
What is the role of flat connection?
What is a what?
Role of flat connection.
A row?
What does it do?
The row of, you're gonna see soon. So we need flat connections and monodromy automorphisms for K1 group to understand K1 in terms of cobordisms. Exactly, that's right.
What do you mean by bending the foam?
Like bending, like literally just bending it, pushing it the other way, moving things around. Like what you have seen before.
For K0, it also identified the isomorphic ones together, right?
Huh?
For K0, it also identified isomorphic ones together.
Exactly. So this is a circle with a flat connection and then with fiber P. So over each point, you have this projective module P assigned over each point. And then it's encoded by automorphism alpha. So when you go around the loop, alpha, you have this automorphism, which is basic monodromy, which is the same thing as automorphism. Monodromy, a flat connection along this circle. Okay, so now let's talk about K1 group. For K1, it's an abelian group, and then now these guys are generated by P comma alpha. P is a projective module, alpha is a monodromy with these two relations. So the relations are, if you have over a point, you have a projective module together with a monodromy, plus a projective module with another monodromy. That's the same thing as the same projective module, and you just compose the monodromies, alpha composed with beta. And then the second relation for the K1 group, whenever you have a short exact sequence, P1 goes to P2 goes to P3, and you have this monodromy, which is like the automorphisms, and the diagram commutes. Alpha 1, alpha 2, alpha 3. So in K1, what we're going to do is we see the middle guy here, P2 comma alpha 2 with the monodromy alpha 2. That's equal to P1 alpha 1 plus the one on the left plus P3 alpha 3, the one on the right. K1, this is also isomorphic to the quotient group, GLR modulo the commutator. GLR is a direct limit of GLNR, and then you just push n to infinity. And element of GLNR, it gives us an automorphism of the free module, R to the n. So for field K, the group, the K1 over a field, this is isomorphic to K star. Because what we do is whenever you see this pair, projective modular together with monodromy alpha, what we do is we associate to that determinant of alpha. And that's just going to be element of K, a unit, K star. So a point, and that's because projective K modules are free. Whenever you have a point with K to the n, what we do is we just assign the rank, and that's for K0. And then whenever you have a circle with the pair K to the n together with the monodromy alpha, you assign to that determinant of alpha, which is in K star. So whenever you see zero-dimensional objects, that's before you assign to it K0. You can think of it as K0 is determined from each other over a commutative ring R. And the one-dimensional object plus a monodromy will give us K1. Let me skip this because I think let me skip this. We're just talking about some K1, some properties of K1. But the first relation that you've seen before, basically it's given by this cobordism here. So you have a circle, which is you have this monodromy. You have over each point on the circle is labeled by projective module P, and then the other circle too, and it goes to the circle upstairs. And then remember, if you think about the first relation, you saw P comma alpha plus P comma beta, and it goes to P with alpha composed with beta. So this is exactly the cobordism. The first relation is given by this cobordism. If you want to, you can keep taking slices, horizontal slices like this, and just move on up until you hit like this guy here. So you might sort of see two circles touching each other. That just means you do alpha followed by beta, right? So that's given by this. So monodromy along the bottom, you have monodromies alpha and beta, and the monodromy along the top circle is just given by alpha composed with beta. The second relation, if you guys remember, we saw short exact sequence, right? Goes from P1 to P2 to P3, and you have alpha maps going downstairs, alpha 1, alpha 2, alpha 3. These are the monodromies. So basically the picture is given by, in terms of cobordisms, you have P1, all the points on the outside surface, that's given, all the points here are labeled by projective module P1. All the points inside, they're labeled by P3. And then arrows pointing from the P1 surface to P3 surface, because it doesn't matter which one comes first in the short exact sequence. So that's why these orientations matter. P1 surface, P3 surface, and they merge towards P2 surface. That's exactly the second relation in the K1 group. Again, now let's take a slice, like just take a horizontal slice, and you should see two circles like this. You have a P1 with the monodromy alpha 1, P3 with monodromy alpha 3. And then upstairs, when you take a slice, you should see P2 with monodromy alpha 2. The last picture on the right, if you want, you can also take a slice, like vertically. Vertically, and what you see is P1, like a line corresponding to P1, projective module P1, another line corresponding to the projective module P3, and then merge towards P2. And then the arrow tells you which one comes first in the short exact sequence. Yeah, so this is for K1 group. Basically, in the next couple of slides, what I do is I explain why the two torsion subgroup appears, and then the reason why it appears gives us, this is our main theorem. So the cobordism group that you've seen, and those were decorated one foams, they're isomorphic to the K1 group, modulo this two torsion with this torsion subgroup. That's basically what's going on. There's a little bit of technicality. But I'm gonna skip through too much details. Is this supposed to happen?
No.
43 is missing. Okay, it's okay. It's okay. So the K1 K1 of projective modules, finitely generated projective modules over a commutative ring R is isomorphic to the cobordism group of 1 foams in the plane carrying a flat connection with fibers being finitely generated projective R modules. So basically, whenever you have crossings, we could turn them into automorphisms and the monodromy, and that's going to give us K1 group, just as what you've seen before. Constructions are very simple. So what you've seen in the second part of the talk in the K-theory paper, you saw zero-dimensional foams, which are points and projective modules. They give us K0 group. For the 1 foams with edges and flat connections and then a monodromy, they give us K1. For the 2 foams, what you should have would be facets, and the higher dimensional gluing will give us K2. And then for n foams, it should give us Kn of R. I would say making this, even though David Gepner thinks we already did everything in our paper, but it's only a paragraph long. It's very short. And Mikhail Khovanov hates it. He wants all the details to be fully written out. So I'm going to say it's an open problem. It's completely open. Do this for K2, K3, and everything. Even for K, the negative integers, K sub minus 1, K sub minus 2, just do it for everything. So all of those are open problems. Because that's what the journal wanted. They want the full detail. They just didn't want like a short summary. But so why is this interesting? We have higher dimensional foams and higher K theory merging. The stories appear to merge together. Constructions are so simple. And then they merge, but someone needs to write this all down. Someone should try to put pieces together. And then what you see is you have new flavors of K theory appearing in terms of foams and cobordisms. So here's an open question. How much of algebraic K theory can be seen geometrically through singular cobordisms? Singular cobordisms because you have lines that are merging, faces that are merging, right? Surfaces that are merging together. So you've seen at the very beginning, you saw lines with weights, or you have vertices with weights, and plus and minus signs. That gave us SAF invariance, and then that gave us the scissor congruence, and then K theory. And this is the end of my talk. Thank you so much for your time. Yes, question?
I didn't see where scissors congruence.
Scissors congruence, it sort of appears in the SAF paper where things are, you can sort of think of it as an interval. You cut it into many pieces, permute things around as much as you want, and glue the whole thing back together. And that's where like the 1 skeleton appears, or the 1 foams appears. Right. Yes. But I'm pretty sure this can be much more further developed in both SAF invariants, like a dynamical systems direction, as well as K theory direction. They both can be pushed out and worked on further. So that's just my motivation. The things do merge, but we just need more people to work on both of these papers that continue on. Are there any other questions? Yes.
So your weighted 1 forms up to cobordism are R wedge product over the integers with
Yeah,
R.
yeah.
And that happens to also be K1
Yeah.
of 1-dimensional scissors congruence.
Mm-hmm.
Do you expect that will continue to the higher K groups as well? In particular, would you expect K2, would you expect weighted 2 foams up to cobordism to be 3 copies of R, wedge product over the integers?
Oh, for the 3 cobordisms or higher cobordisms?
For weighted 2 foams up to cobordisms by weighted 3 foams. Do you have
Oh.
an expected answer for that?
I have to I worked out the details back in March this year,
Yeah.
at the end of March, for K2, nothing else.
Yeah,
But
like K2
yeah.
of weighted foams.
Yes.
Where you got the SAF invariant.
Yes, but I'm not. I would say like I'm not exactly sure if that would sort of work
Okay.
out together. It could. They could work out together.
I'm interested to hear more about that.
Okay.
Any more question? Now let's thank Mee Seong again.